China has unveiled the Hanyuan-2, claiming it is the world's first dual-core quantum computer with 200 qubits. This headline suggests a massive leap in raw computational power, yet the real stakes are far more dangerous. We are standing on the edge of a narrative that promises immediate autonomy for robotics, while the hardware lacks the thermal stability and error correction required to actually move a physical arm. By the end of this discussion, you will understand why qubit counts are a distraction and why the only path to real-world robotics remains a hybrid architecture where classical systems do the heavy lifting. The claim of a dual-core quantum processor with 200 qubits sounds like the definitive breakthrough for autonomous systems. It implies that we have finally reached a scale where quantum mechanics can outpace classical logic for complex decision-making. But here is the thing. In the world of quantum computing, the number of qubits is the least interesting metric we have. A 200-qubit system that cannot maintain a stable state for more than a few microseconds is functionally useless for a robot trying to navigate a cluttered room. The academic consensus is clear. Raw qubit counts are decoupled from effective computational depth because of thermal crosstalk and mechanical instability. Consider the physics of a neutral atom platform, which the Hanyuan-2 reportedly utilizes. These systems use lasers to hold individual atoms in place. While they offer high controllability, they are incredibly sensitive to environmental noise. Every photon that interacts with the atom introduces a risk of error. Every fluctuation in temperature causes the atoms to jitter. This jitter creates a phenomenon called decoherence. When decoherence happens, the quantum information is lost. The system reverts to a chaotic state. For a robot, this is catastrophic. A robot cannot pause to wait for a quantum calculation to finish if the calculation fails every time because the atoms lost their quantum state. This brings us to the critical gap between claimed efficiency and actual utility. The reports on the Hanyuan-2 highlight incredible power efficiency. They suggest that running 200 qubits consumes less energy than traditional supercomputers. But efficiency is meaningless if the system cannot sustain a coherent operation long enough to complete a task. Think of it like a race car engine that burns less fuel but stalls every time you try to accelerate. The engine might be efficient in theory, but it will never win the race. The lack of standardized benchmarks for this specific hardware means we are operating in a data vacuum. We do not know if the claimed efficiency holds up under the rigorous demands of autonomous operation. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Now consider the mechanical constraints that define near-term quantum devices. A robot requires real-time sensor fusion. It needs to process visual data, LIDAR inputs, and tactile feedback simultaneously to avoid obstacles. This requires a control loop that operates at microsecond speeds. Quantum processors, however, lack native low-latency control loops. They are designed for specific optimization problems, not for the continuous stream of data that a robot encounters. Without a classical coprocessor to handle error correction and state estimation, the system cannot react to environmental perturbations faster than the quantum coherence time decays. The quantum unit is too slow to be the brain of the robot. This leads to the architectural necessity of a hybrid approach. The prevailing model in the industry is not a standalone quantum robot. It is a hybrid pipeline where quantum processors function as specialized coprocessors within classical high-performance computing environments. The classical system manages the real-time thermal regulation, error correction, and low-latency actuation. The quantum unit acts as a specialized accelerator that handles specific optimization tasks, such as path planning or complex molecular simulations. This synthesis challenges the narrative of immediate quantum dominance. It suggests that without verified performance benchmarks and robust error mitigation, classical coprocessors will remain essential for the foreseeable future. Let's look deeper into the failure modes of these systems. Production failures in quantum systems are dominated by decoherence from thermal noise rather than the sheer number of qubits. If the Hanyuan-2 cannot maintain logical stability long enough to execute a multi-step robotic maneuver, the power efficiency of its 200 qubits becomes irrelevant. A robot that freezes because its quantum brain overheated is not a breakthrough. It is a failure of engineering. The industry has learned that quadrillion times faster claims apply only to specific, narrow synthetic problems. They do not apply to the messy, unpredictable reality of autonomous systems. The confusion between computing power and deployable hardware is the real danger here. We risk investing in hardware that will be obsolete before it ever works. The narrative of a world-first dual-core quantum computer masks the lack of sustained coherent operations required for complex robotics tasks. We are seeing a shift toward measuring quantum utility by error reduction and circuit depth rather than scale. This is the metric that matters. Until we have a system that can maintain coherence long enough to run a complex algorithm without constant classical supervision, the quantum processor will remain a laboratory curiosity rather than a robot brain. The open loop we started with is finally closing. We asked if the Hanyuan-2 represents a paradigm shift for robotics. The answer is no. It represents a significant step in quantum research, but it does not solve the fundamental constraints of thermal noise and latency. The real breakthrough will not come from a single quantum processor. It will come from the seamless integration of quantum accelerators with classical control systems. The classical systems will handle the 99% of decision-making that requires speed and reliability. The quantum units will handle the 1% of tasks that require massive parallelism and optimization. This is the only path forward. We must separate the hype from the reality. The label of World First is a marketing tool, not a technical guarantee. The engineering reality is that thermal and mechanical constraints make standalone quantum controllers unsuitable for robotics today. The power efficiency claims are unverified against the demands of autonomous operation. The lack of standardized benchmarks creates a significant data gap that prevents us from making informed decisions. We need to focus on error mitigation and circuit depth. We need to build hybrid systems that leverage the strengths of both classical and quantum technologies. The future of robotics is not a quantum revolution. It is a hybrid evolution. Classical hardware will remain the backbone of autonomous systems. Quantum processors will be the specialized tools that sit alongside them, solving specific problems that classical systems cannot. This is not a limitation, it is a pragmatic engineering solution. It acknowledges the current state of technology while leaving the door open for future improvements. Until the quantum hardware can match the reliability of classical systems, the hybrid model is the only viable path. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.